So this is the first part on the unit on acids and bases, and it's really just a revision of this material that you've done in first year. So what you're going to look at is Brønsted acidity, characteristics of Brønsted acids, Lewis acidity, and reactions and properties of Lewis acids and bases in this unit. On this slide, we just have a table giving you some history of the development of the acid-base definition over some period of time. You can see that way back in 1776, Lavoisier showed that some of the oxides of nitrogen, phosphorus, and sulfur react with acid. And as you go down the table, you can see some development of how acids and bases have gone until recently. Okay, so this is just a reminder of the Brønsted acid and base definition. You should be familiar with this, and you should be familiar with writing equations for acids and bases, and you should also be familiar with the fact that water can act as both an acid and a base, and therefore it is classified as being amphiprotic. With regards to the definition of Brønsted-Lowry acids and bases, this information should be familiar to you. I encourage you to stop the slideshow and the video at any point to just refresh your memory about conjugate acids and bases, and please make sure that you are able to do the examples listed on the slides. These are part of the course material, so the revision that you're going to do is going to be tested again in this module. With regard to acid and base strength, you should be familiar with the acidity and basicity constants Ka and Kb. You should also be familiar with the pH scale and how to calculate the hydronium ion concentration. You should be familiar with the general acid equation and how Ka is related to H3O+. You should also be familiar with the one for the general base equation down here, where Kb is related to the OH- concentration. And of course that we know that the acid dissociation constant, if it's much less than 1, is classified as a weak acid. I do expect you to be able to do equations like example 4.2 and self-test 4.2 in the textbook for this module as well. Okay, so you're familiar with the acid dissociation constant, that you've got a weak acid and you've got a conjugate base, how the strong conjugate works, and you need to remember a number of things. Remember too that if you see this P scale, any value of P, it means the minus the log of. Okay, so if we write P in front of anything, it just means that we have minus the log of whatever is going to be written after. So you must be able to do calculations involving equilibrium of acids and bases and any other calculations that you've done from your first year material. Okay, this slide simply shows you some information regarding the acid and base strengths and the related values. So we know that if the acid dissociation constant is much greater than 1, that means that its pKa value is much less than 0, which is indicated in the table on this particular slide. Once again, stop the video at any point so that you can have a look at this table. Remember that interpretation of data forms an integral part of the work that you do in this module. Let's talk quickly a bit about polyprotic acids. Polyprotic acids lose protons in succession. They are acids that have more than one proton, and they have successive deprotonations. And what you will find is that these become increasingly less favorable due to an increase in negative charge. So let's have a look at an example. We have an example here of phosphoric acid, where you see the first proton is lost around about pH of 2, the second proton around pH of 7, and the third proton around about pH 13. And these protons become more and more difficult to lose because the corresponding anions that are formed as a result of a loss of a proton become more and more negative. There are some factors governing the acid and base strength. This is a new concept for some of you. It's called proton affinity. What is it? Proton affinity is actually the negative of proton gain enthalpy. So let's put up a diagram so that you can see what happens is when we take an acid and we split it into its various components, H plus and A minus, what happens is that we get at this point a few things taking place, and we get the proton gain enthalpy, which is actually equivalent to the proton affinity. All right, so we have some figures in the table here which gives you an idea. So proton affinity is like electron affinity. It just means how much energy is required for the material to gain a proton. In this case, you can see the table given for the various conjugate acids and bases that are present. Okay, for acid strength, we find that with electron affinity, we know that electron affinity is going to increase going across a period, and subsequently that means that the proton affinity is going to decrease going across a period. Okay, and similarly, the acid bond strength will decrease going down a group, and subsequently proton affinity will also decrease going down a group. The other factors that we need to consider with acid and base strength is the effect of solvent. Okay, so you remember that some of the ions, like you can see in this diagram on the right-hand side here, they're surrounded by solvent, and that's going to affect how strong an acid or a base is going to be. And so we need to consider all the thermodynamic effects. So you'll remember from first year chemistry, the free energy, the entropy. We can't ignore any of that during the solvation, and it's going to affect the acid and base strength accordingly. One more thing to remember is that most strong acids fully dissociate and generate the hydronium ion when we react with water. So we can generally think of these solutions generally behaving as solutions of the hydronium ion. Water is said to have a leveling effect, which means it brings all the stronger acids down to the acidity of the hydronium ion, and essentially we can work well with strong acids and bases based on this fact.